Hello everyone, this is Yonggan Fu from Rice University. Today I will present our work InstantNet, that is, automated generation and deployment of instantaneously switchable precision networks. Here's an overview of my presentation today. I will start from the background and motivations, and then go through the main contributions, the proposed methods, and the evaluation results of our work. I will start from the background and motivations of our work. We know that big data and big computers have empowered the breakthrough performances achieved by DNNs, which have also fueled a tremendous demand for intelligent IoT devices, such as smartwatches and intelligent wearables. However, there still exists significant challenges for the deployment of intelligent IoT devices. First, as SOTA DNNs become more and more complex, there's a large gap between the limited resources like battery power on IoT devices and the prohibitive cost of complex DNNs. Second, IoT applications often have dynamic energy constraints. For example, they may trade some execution performance for longer running time when the battery power is low, while most of existing works only provide static solutions with a fixed performance energy trade-off. Recently, the switchable precision networks, that is, SPNets, are proposed to tackle the two limitations through enabling DNNs with the capability to instantaneously switch the inference precision at runtime while maintaining the accuracy. However, they only provide a training recipe for a predefined DNN model, while we know that the model structures and the data flows are also major performance determinators for deploying DNNs to IoT devices, which are neglected by SPNets. To this end, our work makes the following contributions. First, we propose the InstantNet framework, which is an end-to-end framework that automates the development and deployment of SPNets. Second, we develop switchable precision neural architecture search, that is, SPNAS, with a Cascade distillation training scheme to search and train better SPNets. Third, we propose an AutoMapper to automatically search for optimal data flows given the SPNets searched by SPNAS under each bit-width and target device. Here's an overview of the InstantNet framework. Given the user demands about the accuracy and energy, and the constrained hardware resources, our InstantNet framework first conducts SPNAS to search for an SPNet with potentially decent performance under different precisions, and then trains it with Cascade distillation training towards the decent accuracies under all precisions, and finally maps the searched network to the target hardware platform with optimized data flows via the proposed AutoMapper. Next, I will give a brief introduction about the three components here. First, InstantNet aims to maintain a decent accuracy under all bit widths, which should be comparable with the accuracy of the independently trained DNNs under each bit width. However, we find that the bottlenecks in SPNets are always the lower bit widths, which suffer from larger accuracy drops when jointly training with other bit widths. To this end, we propose the Cascade distillation training, which distills the knowledge from all higher bit widths to guide the learning of current bit widths. In particular, the total objective function consists of n losses for each of the n target bit widths. The loss for each bit width has two components. One is a commonly used cross-entropy loss, and the other is a distillation loss between the current bit widths and all higher bit widths. Note that here we stop the gradient for the high bit width branches and only update the current bit width. The motivation here is that the quantization noises of SPNets under adjacent or closer bit widths are smaller, so that the distillation scheme in a cascade manner can help more smoothly enforce the bottleneck bit width, that is the low bit width, to approach their high bit width counterparts. Next, to automatically generate the SPNets, which naturally favor working under various bit widths, we propose the SPNAS, which is a differentiable NAS method with a heterogeneous scheme for updating the weights and architectural parameters. In particular, we update the SuperNet weights with the Cascade distillation training and update the architecture parameters only based on the weight under the lowest bit width, which is a bottleneck in SPNets. In addition, we explicitly introduce the hardware cost into the loss function to satisfy the efficiency requirement of the searched SPNets. The third component of our InstantNet framework is AutoMapper, which automatically generates the optimal data flows given the searched SPNet and the constrained hardware resources. In particular, our AutoMapper interprets the DNN execution as a for-loop-based representation and explores a comprehensive data flow search space, including the loop size and loop order across different memory hierarchies, including the DRAM, global buffer, network on chip, and register files, via an evolutionary search algorithm. Our AutoMapper can automatically generate the optimal data flow for each target position for maximizing the efficiency during runtime position switch. We adopt the tournament selection algorithm when searching for the optimal data flow as shown here, and more details can be found in our paper. Next, we evaluate the InstantNet framework and its components with extensive experiments. We first evaluate Cascade distillation training on top of ResNet 38 and ResNet 74 on CIFAR10 and CIFAR100 dataset. In particular, we compare the accuracy of SPNets trained by Cascade distillation training with the accuracy of the corresponding networks independently trained under each position. We can observe that Cascade distillation training achieves a better or comparable accuracy over independently trained position on both network and datasets. We also compare our Cascade distillation training with other SPNets training schemes and find that our method is particularly capable of boosting accuracy in lower bit widths. We next evaluate the effectiveness of SPNAS via comparing it with two variants, that is, full precision NAS and low precision NAS, which quantize the SuperNet to the highest and lowest precision in the candidate precision set during the NAS process, respectively, to see whether the proposed heterogeneous scheme in SPNAS can identify better SPNets. We can observe that SPNAS consistently outperforms the variance at the lowest bit width, which is the bottleneck of SPNets. We then benchmark the proposed AutoMapper with SOTA expert-crafted designs, including DNN Builder on FPGA and Iris and Magnet on ASIC for accelerating AlexNet and VGG16, and we can find that the AutoMapper's suggested data flows outperform SOTA expert-crafted designs with a notable EDB reduction. Finally, we benchmark InstantNet with SOTA SPNet systems, that is, MobileNet V2 trained by two SOTA SPNet training schemes, accelerated by DNN Builder on FPGA across CIFAR10, CIFAR100, and the ImageNet, and we can find that InstantNet-generated systems consistently outperform the SOTA baselines in terms of the trade-off between accuracy and efficiency. For example, 1.86 times improvement in terms of the frame per second with a comparable accuracy on ImageNet. Here's a summary of the contributions of our work. For more details, please refer to our paper. Thanks.